first let's look at what we did in lecture number 15. In lecture number 15, we studied the quantum theory of parametric down conversion. Parametric down conversion, as we saw, is a nonlinear optical process in which the nonlinear medium absorbs a photon at frequency omega 1 and emits two photons, one at frequency omega 2 and the other one at the difference frequency omega 3, which is omega 1 minus omega 2. The photon that is absorbed is called the pump photon, and the emitted photons are called the signal and the idler photons. We saw that this is a very rather inefficient process and is stimulated by the vacuum modes that are there. We derived the interaction Hamiltonian for this process, and it is given by this kind of an expression, which is epsilon naught chi 2 EP plus ES minus and EI minus integrated over whole space, and whole space is the space of the nonlinear medium. EP plus is the positive frequency part of the pump field, ES minus is the negative frequency part of the signal field, and so on. And these are the field operators. And chi 2 is the second order nonlinear susceptibility, and here we are considering a medium that has finite chi 2. Then we looked at the process in which the directions of the down converted photons were fixed, and if we fix these directions to be in this direction, then the interaction Hamiltonian is given by this one-dimensional integral instead of this three-dimensional integral. So of course in general it would be a three-dimensional integral, but if we constrain the direction of signal idler to be in the z direction, then that's the Hamiltonian that will be applicable for the process. So this is just dz chi 2 EP plus zt ES minus and EI minus. So that's the Hamiltonian, and using this Hamiltonian then we derived the two photon state that is produced by parametric down conversion, and here is this state that we derived. Omega s this represents the state of this represents a signal state consisting of one photon at frequency omega s. Omega I, this sub I, that represents the state of an idler photon at frequency omega I, and here we have this integral over omega s and omega I. V is the pump field amplitude that we have, and we consider the pump classically, and this phi is what's called the phase matching function, which is what we are going to study in a little bit more detail today. So this is called the phase matching function, and this phase matching function is essentially an integral this quantity over the length of the crystal, since we are doing a one-dimensional situation kind of problem here. So this is if this is a non-linear crystal, then it goes from the of thickness L, then it is an integral over this thickness L of this quantity. So this is called the phase matching function, and it decides the efficiency of down conversion as to how efficient the down conversion is going to be. Then we also did a change of variable and expressed this integral in terms of omega p and omega d instead of omega s and omega I. And within that, we then considered a pump which is just a monochromatic. That means just the pump frequency was just a single omega naught, and in that case this just becomes a single integral instead of a double integral, which is what it is when the pump is polychromatic. But when pump is monochromatic at frequency omega naught, then this two photon state can be written like this, where we have this phase matching function, and these are the signal idle states in terms of the omega p and omega d. And here we then noted that this is an entangled state, because this integral, which is an integral over omega d, this cannot be separated as just as a state of signal and a state of idler, and hence since this is an inseparable state, this is what is called an entangled state. But the entanglement aspect of this two photon field produced by parametric down conversion, that we will look at in the later lectures, but today we are actually going to focus on this phase matching function, which decides what is the efficiency of this down conversion process, what are the parameters, the crystal parameters or the pump parameters that affect the phase matching, and which way these parameters actually affect the phase matching. So these are the things that we are going to study today. Okay, so for this phase matching, there is a very detailed description given in this paper. This is at the very tutorial level. So I'm pretty much following this paper for the phase matching part. So for more details, one can actually follow this paper. So phase matching, as we define, is an integral of this quantity over the length of the crystal. So this is kpz minus ksz minus kiz. This is the pump wave vector in the z direction, signal wave vector in the z direction, idler wave vector in the z direction. So this is just the difference of this quantity. Although it looks very simple quantity, but it is actually not, which is what we will see in a moment. Here, since we are considering the directions to be fixed, although this I'm showing as an angle, but here we are pretty much considering things that is almost collinear to the z direction. So sometimes we can also write this phase matching function as phi omega s omega I qs qi, just to show at what directions we are talking about of this phase matching function. Okay, so the condition for perfect phase matching is that kpz is equal to ksz plus kiz. That means this quantity is 0. So when this quantity is 0, this exponential is 1, and that's when we get the maximum of this integral. If this quantity is finite, or as this this quantity becomes greater than 0, there will be less and less coming from this integral. So that is the condition for perfect phase matching, and pictorially we can understand this as if this is the kp, that the wave vector of the pump, this is the wave vector of the signal and wave vector of the idler. Then if the kp is equal to ks plus ki, then we can get the perfect phase matching. That's a one way in which we can achieve this condition. The other way also is if we have ks and ki like that, such that this since kp is a vector, so we can also have this kind of condition in which we can also satisfy the phase matching. So essentially the point is whatever are the conditions that lead to kpz being equal to ksz plus kiz, then we say that the phase matching is satisfied, and that to the extent that the phase matching is satisfied, the value of this phase matching is greater to that extent, and to that extent we get the down converted photons generated. So even when these two are not exactly, kpz is not exactly equal to ksz plus kiz, this quantity is still finite, but of course it won't be, the phase matching and the down conversion will not be as effective as it is when this quantity is equal to 0. So there are several factors that affect the phase matching, and if, for example, frequency, wave vector, the crystal length, and so on, and also the polarizations of the signal, idler and pump. But so far we have been treating it the fields as a scalar field, and we'll continue doing so. But we cannot ignore the polarization effects in phase matching, because the wave vector and the refractive index of a wave or a field inside a nonlinear medium or birefringent medium depends on the polarization as well. But here we will actually separate the polarization effect. We'll study the polarization effect separately than the other effect. So in parametric down conversion, the possible phase matching scenarios as far as polarization is concerned, that we have listed here. So for there can be two types of medium or crystals, what's called the positive uniaxial crystal and what's called the negative uniaxial crystal. So let's say if we look at negative uniaxial crystal, then there are several phase matching scenarios as far as polarization is concerned, with which the phase matching can actually be satisfied. So for example, if the pump photon is extraordinarily polarized and the signal idler are both ordinarily polarized, then it's called the type 1 phase matching. So if we insist that this one pump is extraordinarily polarized and both the signal idler are ordinarily polarized, then we can satisfy the phase matching. We can also satisfy the phase matching when signal idler are oppositely polarized, that one is extraordinary, other one is ordinary, and vice versa. And so these two other conditions are called the type 2 phase matching. So we can satisfy this phase matching when the pump signal idler are in this combination. We can also satisfy the phase matching when the pump signal idler are in these combination, that is type 1 and type 2. So these are the different phase matching scenarios that we can have as far as polarization effects are concerned. So we will just take one of these scenarios, that means let's say type 1 or one of these type 2 conditions, and then we'll look at what are the other effects that are responsible for phase matching. So just a quick point here that in the lab, what people mostly produce parametric down conversion with is with this negative uniaxial crystal, and one of the very famous negative uniaxial crystal that is used for the production of down converted photon is called the beta barium borate. But this is just one example. There are several other crystals, but this is the one that is quite widely used. Okay. So that's the phase matching condition. This is the and then to satisfy it, we just need to see that this is 0. That's the perfect phase matching. But even when this is not 0, then the phase matching will be not perfectly satisfied, but it will still have some efficiency. And we now want to see how it actually depends on different condition. So although it's a very simple expression here, Kpz minus Ksz minus Kiz, but for type 1 phase matching, we see that this Kpz is given by this kind of an expression. I actually don't want to go through the details of it. If somebody is interested, you could actually look up this reference. But the point is, this Kpz is quite a complicated expression that depends on so many parameters. There's alpha, beta, gamma over here, and these alpha, beta, gamma then have, it actually depends then on the refractive index of the photon and whether it is ordinary polarized or extraordinary polarized and so on. So for type 1 phase matching, we know that the pump is extraordinary and the signal idler are ordinarily polarized, and then all these conditions, all these factors will have to take into account in order to calculate this Kpz, Ksz and Kiz. One quantity that I want to point out here is this theta p. So this theta p is the angle between the direction of the pump and the optic axis of the crystal. So if this is the pump direction and if that is the optic axis of the crystal, so this angle between the optic axis and the pump is called the theta p. N is the refractive index of the light. NPO is the refractive index of the pump photon when it is ordinary polarized, refractive index of the pump photon when it is extraordinary polarized, and so on. Okay, so with that, you can also look at one other effect as to how it actually affects the down conversion. So that is the effect of non-normal incidence of the pump field. This is pretty much same as changing theta p, and that's how it works. So if we have a crystal, and if we have this pump photon coming in at this crystal, suppose this crystal is, if the crystal is oriented in such a way that the pump is coming to the crystal at normal incidence, then of course it just goes like this. But if the pump is tilted with respect to this incoming, if the crystal is tilted with respect to this incoming pump at an angle alpha, then there will be a refraction of this pump inside the crystal. So if alpha is the angle of incidence of the pump field, then the beta is the angle of refraction, that's the angle of refraction, and then we can calculate and show that this beta is sine inverse sine alpha NPE, and then in that case this theta p that we are talking about, which is the direction, which is the angle between the optic axis and the direction of the pump inside the crystal, this will then change as a function of this alpha. So this theta p is then depends on what this angle alpha is, that is at what angle the pump is incident onto the crystal. So as we can see, as we rotate the crystal for an incoming pump, as we rotate the crystal, we introduce this alpha, and we introduce this alpha, then we are changing theta p according to this relation. So this is actually one way of changing theta p. By just rotating the crystal, we can actually change theta p, and by then changing theta p, we can get closer to the perfect phase matching or go away from it. Okay, now let's look at some numerical simulations of phase matching. This is to give some intuitive feeling of what actually we see in the lab as far as this phase matching and the production of down converted photons are concerned. So here I'm doing this with realistic parameters. So here we have a beta barium borate crystal. We have a laser 405 nanometer, and it has 100 milliwatt of power. We are using I'll show some experimental results as well. We are using an EMCCD camera. This is the camera that detects single photons with 512 pixels. The length of the crystal we are using is 2 millimeter, and the pump that we are using has a beam waist of 388 micron. This is not a very important parameter here, but this basically is the pump beam waist location from the crystal. So when the theta p is 28.64 degrees, this is the numerical simulation based on this equation. We are just evaluating this equation with all these big expressions. So when theta p, that is the angle between optic axis and the pump direction, when theta p is 28.64, this is what we see at some point on the screen along z. So this is just a blob. If we increase theta p to 28.74 degree, then we see the this blob turning into a ring. If we increase it further, then it becomes an even bigger ring. In fact, before 28.64 degree, there is really no down conversion. So we say that the phase matching is starting to get satisfied from around this angle. So we did actually an experiment with these same parameters, and these are the experimental results, and we see that these are matching quite well. So this is when we change the this is when we have the theta p from 28.64 to 28.95. That's a pretty small angle range. So if we just keep on increasing theta p, let's say we go at theta p equal to 40.48. So it turns out that starting from 40.48, we can actually have type 2 down conversion conditions being also satisfied. So that's in the type 2 case, we actually get, instead of one blob, we actually get these two blobs. And if we increase the theta p from there, then we see that it is the two individual blobs become like a ring. If we increase theta p even further, then these rings start to kind of touch each other, and by going even further, we see that they now overlap. So these are the type 2 phase matching condition. That means this one is ordinary polarized and this one is extraordinary polarized, or vice versa. We can have it in any manner. So again, the phase matching starts at about 40.48 degree of theta p, and then from this point on, which starts as a blob, we see the ring, and then that starts touching and then starts overlapping. Just a very quick comment here, that these two overlapped points that we see, if we just pick up these 2 points, that actually gives entangled photons entangled in the polarization basis. This is because this is extraordinary polarized ring, this is the ordinary polarized ring. But if we look at these two spots only, then if we see, if we detect that this one is ordinary, then this one becomes extraordinary, and vice versa, because these are the overlap points. So we don't know which, if you see an ordinary, we don't know which way it actually comes. So this is the, if you just pick up photons from this point and that point, this becomes a source of polarization entangled photon. This we will discuss in more details later, but I just wanted to kind of point it out here. We also did an experiment where we can see very similar effect, but here we see the background is quite something, because this crystal that we were using is actually meant for type 1. And if we rotate the crystal to 40, although one can see the phase matching, but because of the too much angle, there's a lot of scattering that we have. But instead of, other than the scattering, we do see all these effects in the experiments as well. So that's the effect of theta p on the phase matching. So then we can also look at the total down conversion intensity in parametric down conversion. So this is the, now we are looking at the total down conversion intensity. So that's the, so for example, this is theta p, and if I look at the total intensity, that is a power that actually comes out. So if the theta p is 28.4, or if it's below 28.6, there is really no down conversion, so there is really no power. Starting from 28.6, the down conversion, the phase matching starts to kind of get satisfied, and then we have some down conversion, and pretty quickly from 28.6 to maybe 28.7, it actually achieves the perfect maximum down conversion efficiency, and from then on it remains pretty much flat. Although the size, we know that if we increase theta p, the size of this ring increases, although the size increases, but the total power contained in that ring, that doesn't increase, so that remains flat. So that's the type 1. In the case of type 2, then we have to go theta p around 40.4, and then of course before that there's no type 2 being satisfied. So around 40.4, the type 2 phase matching conditions start to get satisfied, and at that point we start with 2 blobs here, and then if we increase theta p from there on, we have these 2 rings. So again, from 40.4 to 40.6, it achieves the maximum down conversion efficiency, and after that, if we increase theta p, the only effect it has, it just increases the size of the ring, but the total power contained in those ring remains the same. Now let me comment here that when we are at 40, the type 1 is still being satisfied, but as we saw that when we go from 28.6 to 29, the ring already becomes quite big. So if we actually go by 10 more degrees to 40 degree, the type 1 ring has become huge. It is somewhere over there, but it is actually there. So at 28.8, we only have type 1, but at 40, we have both type 1 and type 2. But the type 1 ring is actually huge. So in the lab, when we want to work with the type 1 photon, we work at these angle ranges. When we want to work with type 2 photon, we work at these angle ranges, because this type 1 is then just a huge ring, and so that if we are doing experiment along the z-axis, the detectors on the z-axis actually will not catch those photons, but they are there. We can also look at the maximum intensity. So we looked at the total power, but what about the maximum intensity of these type 1 photons? So for type 1, again, we start 28.6 degree, and the maximum intensity we can see is in the center when it's a blob, and when it becomes a ring, the maximum intensity will be somewhere along the ring, in the center of the ring. So if you just track the maximum intensity point, this gives a function like this. Of course, we know that the total power is kind of independent of theta, as we saw here. Once it reaches a value, a perfect phase matching, then this total power remains constant. But even then, the maximum intensity of the type 1, that actually decreases in this manner. One can also look at the effect of crystal thickness. So this is again type 1, and we are looking at 28.74 degrees. So if it's L equal to 1 millimeter, that is the thickness of the crystal is 1 millimeter, we see it like this. 2 millimeter, this is what we get. 3 millimeter, that's what we get. For type 2, that would be around 40 degrees or something. This is L1, and this is L equal to 2 millimeter, this is L equal to 3 millimeter. So overall, what we see is that the effect of thickness, or increasing the thickness of the crystal, the main effect is that the down conversion gets sharper and sharper. So this is a ring, and if we increase the thickness of the crystal, the ring just becomes sharper. Again, same for type 2. The increasing the thickness of the crystal doesn't increase the size of the ring, it just makes it sharper. So that is the effect of the thickness of the crystal. We can also quickly look at what's called the position correlation width. This we will see more when we are doing the EPR paradox after a few lectures. So here we are looking at, so that's the down conversion that we see. Of course, we know that these are two photon. So of course, if we detect one here, the other one would be over there. Now when we have a ring, if we detect one there, the other one would be over there. So the question is, if we get one photon here, what is the range over which we can get what is the position over which range of position over which we can get the other photon, and that is what we call the position correlation width. So when for this kind of situation, if we detect the photon in the center, then the probability that of getting the idler photon is over this area. In this kind of phase matching, if we detect a photon right here in the signal photon over there of this size, then the probability that we get an idler photon is over this area, and of course this is maximum over here, and it decreases in this manner. And of course here, if we detect a photon here, then this is the area over which we can detect the idler. We look at the one-dimensional plots to get a better idea. So that's the area over which we can get the idler, and that's the probability density of the detecting the idler, or the conditional probability density. So we can see when we go more and more non-collinear, this is collinear, we've got going more and more non-collinear, the position correlation width that becomes more and more narrower. So if we are in this collinear situation, if we detect a photon here, we have a possibility of detecting the idler photon over this width. But if we are here, then we detect a photon over there, then the position over which we can detect the idler is this, which is of course much smaller than this. So for the non-collinear condition, the position correlation width becomes smaller. So this is what we have for phase matching. We have also written a phase matching program in the lab. This is just to get a feeling of how the phase matching works in the lab, and this is This is just a simple program that I have in my lab. Here we can change the different parameters and see how the rings actually change. So for example, this is the pump wavelength is 405 nanometer, pump angle is 28.91. This is pump beam waist, this one is 388. Crystal thickness, let's do 2 millimeter. Then if we just do, that's the ring that we see on a screen that is kept at some distance. We saw that 28.6 we had the blob. So as we can see, this is the down conversion is just starting to get satisfied. So this is pretty bad phase matching condition here. Now if we increase it to 28.7, now this we see the down conversion, the phase matching is starting to get satisfied. Before that it was just no down conversion at all. If we increase it to 90, we see that the rings start to open up, and if we just keep on increasing the theta p, the only effect it will have is just it will increase the size of the ring. Let's do 29. It's pretty big. We can do 30. Is even bigger. So if we just keep on going, this type 1 ring will become bigger and bigger. Now if we go to around 40.6, so here this is maybe let's go a little bit less, 40.4. So at 40.4 we have this type 1 down conversion, but there is no type 2 that has started yet. But again, if we do 40.5 degree, then the type 2 down conversion has just started. And if we increase it further, these blobs will start becoming a ring. Let's make it even bigger, 40.8. Now we can see very clearly see these rings. Let's make it 41.4. Now these rings are just touching each other. Let's make it 41.8, and now we can see these rings are kind of overlapping. So that's the effect of theta p. Now we can also see the effect of changing the thickness of the crystal. If it decreases crystal thickness to, let's say, 1 millimeter, this overall the phase matching remains the same. It just becomes hazier. It just becomes, the rings are becoming more wider. If we just make it from 1000 micron, if we let's make it 500 micron, it will become the phase, because the phase matching is much more relaxed now, and then it is satisfied over much bigger area. So that is the effect of the decrease in crystal thickness. But let's just now do make it 3 millimeter, 3000 micron, and then we see that it becomes much sharper. Make it 5 and it becomes even sharper. So that is the effect of increasing the crystal thickness. So this is the program that we have in the lab. If somebody wants, we can provide access to this program in some limited manner, as much as it is possible. So but this kind of program gives a pretty nice intuitive feeling about the phase matching and phase matching conditions. So we will stop here. Thank you.